So yeah, it may not necessarily be the material as much as it is feeling that pressure. So the only way to prepare for that is to practice it, right? To actually be in that environment. So I would say I gave you, what, 7 minutes? I would say my expectation is that you could probably finish these in 5 minutes, these two problems in 5 minutes. To give you an idea of, like on an exam, how many problems do I put on there? I usually put how many problems I think you can accomplish in the time I'm giving you, right? So it's not necessarily, every student's different, but there's not only an expectation of you knowing how to do it, but knowing how to do it within a certain time frame, all right? Got it? Okay, in my opinion, that was like a 3 or a 2. Like in my opinion, those problems. The first problem, there's really nothing special. It's very, very easy things to look at. The second problem, you had to factor a quadratic, or 2 quadratic functions. So one was a difference of squares, one was just a regular old AC method. There's no fancy algebra there, right? So that's why I would rank it down here like a 2. You did have to factor a negative out, right? That maybe pushed it to a 3, but other than that, I think it was straightforward. So I'm only telling you this because so that you can kind of figure out where you are, right? If I think that's a 2 or a 3 quiz, and you think it's a 9, then something needs to adjust before the 15th of September where you feel more comfortable with something like that. All right? Questions? Questions on homework? Questions on anything else? No? Okay.
I guess on the discontinuous, continuous.
Yes.
The answers that I got compared to the answers that they were giving, I guess I might have been kind of confused about how they were presenting the answer versus how they covered the class.
Okay. So you have an example of a problem?
I didn't really write it down, man.
Okay.
Like even just number 3, the first one.
State where it was discontinuous. So you're saying where the function fails to be continuous.
Yeah, and then it was talking about certain ones that
If it's left or right.
did not exist or something. No, the left or right didn't really bother me.
Okay.
But I don't remember what I should have written down what it had online.
Okay.
I mean, basically, it's x equals -4, there's a hole. X equals -2, there's a hole. X equals 2, there's a hole.
Yeah. Okay. Something like that. Yeah.
Yeah.
Uh-huh.
And they had like 3 more answers on there, and I was like, I don't know. We didn't really have. I think
Like where it
did
went.
not exist.
Okay. So that's where it went to like infinity. Probably that's where it went to infinity.
Okay.
But you know what? I tell you what. If you have questions more on that, let's get together and talk about it so I can be very clear on what you're not understanding.
Okay.
There's kind of an issue with the way the book does things that I've always had a problem with. In 1.4 and actually in 1.3 when we're looking at this idea of coming in from the left and the right, like this. Let's say this is the value 2. And let's say that the function goes up right here and down like this. So if we were to say what's the limit as x approaches 2 from the left of this function, in the beginning of this chapter, all right, they will say that, okay, as you're coming in from the left of 2, right, from the left of 2, you're headed up and up and up and up, right? In the beginning, they say that this limit does not exist. They would say this limit does not exist. But now, today, we're going to say that this limit from the left goes to infinity. So when I start talking in the beginning of the semester, I always just start with infinity because that's where we're going to wind up anyway. So this right here would be infinity because as from the left, it's headed to positive infinity. Now, if we did the limit from the right of this function, where's it headed? Negative infinity, right? And in the beginning, this might be where there might be a confusion, is that they're looking at where you have a discontinuity like this, and they're saying that doesn't exist, where actually it's infinite or not, or infinity or not negative infinity. So that could be it. Any other issues, questions? Yes?
Just a question on something we learned last time.
Yes.
We learned an identity, I guess, Sine junk over junk.
Yes.
1.
Uh-huh.
And also the inverse of that, junk over sine junk.
Yes.
Does the same principle of the inverse apply to the cosine?
Cosine one, great question. Okay, so one of the ones we looked at was limit. Well, I'm not going to do the sine one. Let me get to the one that you were asking about. This one right here. It was cosine x minus 1 over x. I told you that this was equal to 0. And I said it really doesn't matter what the limit's going to. This could be cosine junk over, over junk as long as the junk matches, as long as the junk goes to 0. Then it's just like the sine one, this will be equal to 0. Your question is, can we flip it over like we did with the sine? Would this be the same? Could you say limit x goes to 0 of x over cosine x minus 1? Would that be 0, right? That's your question. And the answer is no. And the reason why is because all we're doing, like this right here, this expression right here is the same as saying 1 over cosine x minus 1 over x, right? That's what this is. Because you do 1 over a fraction, you do the reciprocal, right? So do you agree these two are the same? So if I look at this and I take the limit, the bottom is headed to where? Well, according to this, the bottom's headed to 0, and you have 1 over 0, and that's undefined. But with the sine one, the other one, yeah, so the other one would be, you have sine x over x. We know that goes to 1 when you take this limit. And then the other one, when you flip that over, I told you this is also 1, but again, you can see that because this is really 1 over sine x over x, right? It's this. And then that goes to 1, and 1 over 1 is still 1. Make sense?
Thank you.
Okay, good. Any other questions? All right, so today we are going to cover 1.6, limits involving infinity, all right? So before I even get started in this section, I want us to talk a little bit about infinity, all right? Because it's something we've all heard, right? The word infinity. We all kind of think we have an idea of what infinity is. So infinity, anyone want to take a shot at describing what infinity is? Is it like the biggest number out there, or what is infinity?
Ever increasing number or decreasing?
A number that is just getting bigger and bigger or something? So can you actually say it's a number then? You can't really say it's a number, right?
More of a concept.
It's more of an idea, okay? Infinity is an idea. It's a concept. It's the idea that something is growing without bound, right? It's getting bigger and bigger and bigger and bigger. But it's not a number, all right? Because if you say it's this number, I can always do that plus 1, and now I've got a bigger number, right? So infinity is a concept, right? It's an idea, right? That's what it is. It's an idea, right, that something is growing without bound. When I say without bound, I just mean that it's just going to grow and you're never going to get to a number it doesn't go past, right? It just keeps getting bigger and bigger and bigger. So on a number line, the idea of infinity is the idea that we are going to just continue going out to the right forever, right? If we continue going this way forever, we are headed towards positive infinity, right? So as you go out to the right, the numbers get bigger and bigger and bigger and bigger and bigger, right? Now, what if I go the other direction? Where am I going to be headed to? So if I go this way, growing without bound, but that way, I'm headed to what we would consider negative infinity, right? The idea is that I'm getting bigger and bigger. Listen to what I'm saying. I'm getting bigger and bigger, but negative, all right? This is a language thing we all have to be clear on. Because if I tell you right now that I have a small number, what do I mean?
0.0000000, yeah.
That's what you're interpreting as. When I say small, you're thinking close to 0, right? But haven't you been told in the past that if you take two numbers on a number line, the one to the left is smaller, right? That's what you're taught. Smaller numbers are to the left. So if I take, let's keep going, -7, what's the smallest number of these numbers? What's the smallest number? -7, because it's furthest to the left. So we have to be careful with our language here. What do we mean by small in this class? What do we mean by like that way forever? So to clear that up, I'm just going to just state it right now. When I talk about small here in this class, what I mean is when you take the absolute value of the number, it's close to 0, right? So we're talking about, when I say small, I mean numbers that are close here, all right? I don't mean small to mean way that way. If I want to talk about being way, way down this way, I'm going to say a very large negative number, all right? If I want to say something going this way, I'm going to say a very large positive number. Does that all make sense to you? Questions? Yes?
So is that definition of an infinity accurate? Because, so there's an infinite amount of points between 0 and 1, but it does have a boundary which is 0 and 1. So.
Okay. What you're doing, there's two different things. I'm saying if you talk about infinity, right, as like if you think about a number and I say it's becoming infinite, it means it's growing without bound. What you're referring to is trying to count how many numbers are within a set of something. That's something else, but that's another place where you hear the word infinity, right? So the question was, or the statement was, if you take all the numbers between 0 and 1, right, how many numbers are in here? And you're saying there's an infinite number of numbers in here. Do we all agree with that? I agree as well. If you started counting the numbers, right, you would take one, pick one, that's 1, right? Then you take another one. Here, that's my second number. Take another one, that's my third number, right? So if you keep counting this, you have an infinite number of things, right? What do we mean by infinite number of things? The number of things we're getting is going to infinity, right? I don't know if I'm addressing your...
I think I get what you're saying. So
Okay.
Like our analysis is infinite, but that one, the number line is infinite one. This one is more analytical.
Here, if we're talking about, well, think about a value of x, okay? Think about, let's say we take some value of x. That x could take on any value, right? Like it could take on 0, 1, 2, 3, 1.5, pi, whatever. It can take on an infinite number of values, right? But what happens as x goes further and further down this way? X is growing, right? It's getting bigger and bigger and bigger. So we would say x is headed towards infinity. It's growing. There's a difference between that and counting how many things you have. Those are two different concepts, but they both involve the idea of infinity, right? If I just say start counting, 1, 2, 3, 4, 5, 6, right? You're counting a list that has an infinite number of things in them, right? Right? Yeah?
Yeah.
Okay.
So I guess like the definition would kind of have to change a little bit.
Well, it depends on what we're referring to. Here I'm referring to the idea of a number on the number line becoming infinitely big, right? I'm not trying to define what infinity is. I'm trying to get us to understand, conceptually for us in this class, infinity is the idea that something is getting bigger and bigger and bigger. Whether that be you counting how many things are in here. See, I'm counting, but that list is getting bigger and bigger and bigger forever, right? Infinity is a very strange concept, all right? It's hard to define. There's actually two types of infinity, all right? There's two types. So this is going a little bit beyond this class, but we can talk about it. So with infinity, the two types that we have are, just imagine I start asking you to count, right? 1, 2, 3, 4, 5. That list is going to have an infinite number of things in it, right? We'll go on forever. So that's one idea of infinity. We call that countable. So this list that goes forever, this would be referred to as countable, because you can kind of march your way through these numbers, right? You'll never finish counting, but it goes forever. That's countable or countably infinite. There's another type of infinity called uncountable. So the best way I can explain uncountable is this. Am I ready to tell you all this story? I don't know if I'm ready to tell you all this story or not.
Isn't it just decibels in between those?
Yeah. Okay, so let me ask you this. Let me ask you this. If you were to close your eyes, okay, and reach into this interval 0, 1 and grab a number, right, in that interval, what do you think the probability is that you have a fraction in your hand? So just think about that for a minute. Think about all the fractions in here. 1/2, right? 1/4, right? 3/4, 1/8. How many fractions are in here? An infinite number of fractions, right? There are an infinite number of fractions in here. Okay? Close your eyes, reach in there, grab a number. What do you think the chances are that you have a fraction in your hand? Are the chances really good? Are they 50-50? Is it, what do you think? 100%. 100%? 0. There is 0 probability. There's 0 chance that you have a fraction in your hand, right? And that should be like, what? Right? That should make you go, what? Yeah, so I'm telling you that if you reach in here and grab a number, like blindly grab it, the chances that you're holding a fraction in your hand is 0. Why? Well, because even though there are an infinite number of fractions in here, those fractions that are in here are countable. There's a bunch of other numbers in here that are not fractions. You learn about these numbers, and when you learn about them, they only give you a few examples of them. Does anyone know examples of numbers that cannot be written as fractions? Can someone give me an example of one? Pi. Pi is an example of a number you're taught, this is irrational. Do you remember ever hearing that? Pi is an irrational number. What is a rational number? Ratio, fraction, okay? All the fractions are rational numbers. Anything that's not a fraction is called irrational. Pi is one example. Anyone know another example?
Square roots.
Certain square roots, right? Like root 2, that's irrational. Remember that number e from college algebra? All of these numbers have something in common. If you write them as a decimal, the decimal will continue forever, and there's no pattern to it. Like pi is 3.1415. It keeps going forever. There's no pattern to it. Never repeats itself, okay? Every irrational number has that property. Every one of them. But the bad thing is when you're in school and kind of learning math, they only give you a few examples. What they don't tell you is that the irrational numbers that are in here, just even between 0 and 1, the number of irrational numbers that are in here is infinite. But it's uncountably infinite, meaning that there's not even a way to count them. It's really a weird concept. So here's my best analogy that I can give you. Okay, here's the best analogy I can give you. If you've ever been away from, got away from the city lights at night, has anyone ever actually seen the Milky Way through the sky, like with your own eyes? No? No? It's been a long time for me, but if you get away from the city, you get out at night, you can see all the stars out there. It's incredible, right? And if you look up at this night sky, think about all the stars as being the fractions in here, okay? And we're not going to say there's an infinite number of stars, but the idea, again, is that they're everywhere, right? So you have like an infinite number of fractions in here. The irrational numbers is like the what? Like the dark, okay? It's everywhere but nowhere. It's like you can't even point to the black because what are you pointing at? Does that make sense? That's exactly the way you can look at the rationals and the irrational numbers in here. Stars are the fractions, the black space is the irrationals. So the question I asked about closing your eyes and reaching in there, that's the same as me saying, what are the chances of you closing your eyes, pointing into the night sky with like a perfect line and opening your eyes and that you're pointed exactly at a star, right? Chances are essentially 0. You would have to open your eyes and actually try to point at the star. Does that make sense to you? Yeah? Yes?
So is the chances 0 or like?
It is 0. It is 0. Yeah. This is called measure theory, and you don't get into measure theory until you're like probably junior, senior level math major, because there's a lot of buildup you have to get to this point. Like there's a lot of framework you have to put in place, but we can kind of talk about it here. So anyways, we need to get back to this. the idea of infinity is that something is going to be growing without bound, right? We either have positive or negative infinity. And the fact that there's two different types, we don't need to worry about that. Small for us here means a number close to 0, right? And so 1.6, what we're talking about are limits that involve infinity now, all right? So we're going to start with stuff that we've already seen. I could talk about this all day long, all right? But I have to stay on track here. All right, so I would like to give you an example just to kind of get us motivated with the idea here. Somehow the limit that I'm going to put up on the board here is going to involve infinity. Somehow. So let's do the limit as x approaches 3 from the right of x plus 1 over x minus 3. So what's the first step you do anytime you want to do a limit? Substitute, right? Just plug in 3 for x, right? Now I'm approaching 3 from which side? The right. Well, that doesn't really matter when I do the substitution. I'm just going to plug 3 in and see what I get. So what do I get on top? 4. Okay. What do I get on the bottom? 0. Okay. Now 4 divided by 0 is undefined, right? It's undefined. However, this is not 0 over 0, is it? We've been getting 0 over 0, and that's when we have bad, that's when we need algebra, right? But here, this is different. We don't have 0 over 0. We have on top, does everyone see that this is a fixed number? When I say fixed, I mean it's a constant, right? It's just some number. It's not 0, though. I'm going to say it's a fixed, and then to the right, I'm going to put plus. It's a fixed positive number. So on the top, I've got a number. It's headed towards the numerator, I should say, is getting closer and closer to a positive fixed number 4, right? However, the denominator is headed to 0, isn't it? Headed to 0, getting closer to 0, getting smaller, isn't it? Getting smaller, smaller and smaller. So I want us to think about what happens when you take a number like 4 and divide it by a number that's small.
It's going towards infinity.
It's going to get big, right? Now, I need everyone here to understand that. It's a basic fundamental thing that we all have to agree with. So just imagine I take the number 4. Let's start dividing it by smaller numbers and see what happens. So let's take 4 and divide it by 1. Now 1's not very small, right? But this would be 4. Now let's take 4 and divide it by a smaller number. What's a number smaller than 1? 0.1. 0.1, something like that? 0.1. I'm going to write it as 1/10. Is that all right? That's the same as 0.1? And then when you do 4 divided by this, you just flip the fraction up and it becomes 40. And if I do 4 divided by, let's go smaller, how about 1 over 100? This is going to be 400, isn't it? And do y'all see that the smaller that this gets, right? The smaller the denominator gets, the bigger the ratio gets. Now that's only happening because 4 is always staying the same, right? If this was 0 over 0, totally different ballgame. Totally different method or approach we take to this. But if our numerator is staying the same number and our denominator is shrinking down to nothing, the ratio should get huge, right? Yeah? So the only thing left for me to kind of figure out here is kind of like, I know that this is headed towards a fixed number over 0. I know that it's getting bigger, right? This ratio is getting bigger, but I don't know if it's getting bigger positive or negative. I don't know. It could be getting big in negative or big in positive. So the way to analyze this is to figure out what's happening down in the denominator. So what I'm going to do is I'm going to draw the kind of like way you approach these problems is as soon as you figure out you've got a fixed positive number over 0, you're going to try and figure out whether or not the numerator and denominator are both always positive, or is one of them positive, one of them negative, or are they both negative? You've got to figure out the signs of these. 4 is always positive, right? There's no changing that. But I don't know if this number is getting small and getting small through negative numbers or through positive numbers. I don't know yet. So what I have to do is go back to where I'm approaching. I'm going to draw a number line. Here's 3. I'm approaching from which side? The right side. So I'm coming in from this side. And so I'm just going to think about an example of a number that's to the right of 3, but a little bit bigger. So How about I go with like 3.001, something like that. So I'm just kind of like thinking through this. If I take a number to the right of 3 and I plug that in right here, what would happen? What's 3.001? What's 3.001 take away 3? Right? Take away 3. What would that be? 0.001, but it would be positive, wouldn't it? That's the key. This right here is going to be a positive number because I'm taking a number to the right of 3 and subtracting 3 from it, which will always leave me a little positive piece. Got it? If I took a number closer, like 3.000000001, right? That'd still be to the right of 3, and if I did the subtraction, it would still give me a positive number, right? So I now know that my number on top is fixed and it's positive, and the number on the bottom is fixed, I'm not fixed, headed to 0, and it's always positive as well. And the ratio of two positive numbers should be positive. And I already knew it was getting bigger. So my answer should be positive infinity. See, there's not a whole lot of work you're doing here. You're just kind of analyzing things.
What if you take away the positive off of 3 and you're
I'm gonna do that. Yeah, I'll do that. Question.
Can we just like throw the answer down, or what work do we have to show?
What do you mean?
Like on the test, like what work do we have to show for that? Or can we just write the answer down and that's fine?
I don't know. Before I answer that, let me give you a couple of examples because I think maybe you need to see a few so that maybe you'll believe that you actually do have to do something. You can't just look at it all the time. Maybe. But okay, to answer your question, if you just put the answer down and it's wrong, it is wrong. Okay, like out of 10 points, you get nothing. Now, if you do something and I see, okay, you came in from the wrong side, or when you did this wrong. If I see that and you made a mistake, I take off less. So I guess I would say proceed with caution if you're just going to give me an answer. Be very sure that you got it right. All right? I'm going to answer your question. That's kind of where I was leading. What if we take the same exact problem, but this time we approach 3 from the left? Okay? So same exact thing, right? So you take the limit, right? Direct substitution. The numerator's headed to 4 again. The denominator's headed to 0. So that's exactly what was happening here, right? Exactly what was happening here. So now I look and see, can I figure out what's happening in the numerator? I mean, it's a fixed number, right? And it's always positive because, well, 4 is positive, right? So this is a fixed positive number. And then now, on the bottom, it's headed to 0. And what I'm asking myself now is, can I resolve whether or not this is positive or negative? Like, do I have small positive numbers or small negative numbers? That's what I have to figure out. So I'm going to approach 3 now from the left. So when I draw a number line, I'll do it in blue again. When I draw a number line, if I come in from the left like this, then what would be a number to the left there? 2.999, something like that. And imagine plugging that in here. 2.999 minus 3. That's going to be a very small negative number, right? Negative. So this is going to be negative. And that will always happen if I'm coming in from the left, isn't it? So now I know here that this, which was a question mark, is now a very small negative number. And so when you take the ratio of a positive and a negative number together, you should get a negative answer. And we already knew it was getting big because, well, were we okay with the idea that this is going to be either infinity or negative infinity? Like we know it's getting big because fixed over 0 always gets big. It's just, is it positive or negative? Negative infinity. Let's look at the graph of this. I'm going to look at the graph of this function. I'm going to take...
But what if it approaches from both sides?
Yeah, I'll get that. Yep, that's a good question. X plus 1 over x minus 3. There's the graph. This should look familiar to you. College algebra, that was a rational function, wasn't it? So we call that in college algebra a rational function. And do you see that as we come in to 3 from the right, that was the first example we did, right? As we come into 3 from the right, our function is headed towards positive infinity. And as we come into 3 from the left, it heads to negative infinity. Right? We did that without having to look at the graph. We did it with just using limits. Now, the question about what happens if I didn't put the, what if I gave you this problem and I didn't put a plus here, and I just asked you to give me this limit? Then what would you do? If I don't give you plus or minus here? Well, that means you have to check both sides. That means you have to do 2 different limits. You have to do from the left and from the right, and make sure that they are equal, right? And in this case, they wouldn't be equal, right? So from one side you get infinity, the other side you get negative infinity. So since infinity and negative infinity are not the same thing, we would say what? Does not exist. Does that answer your question?
Yes,
Okay.
Thank you, sir.
Yep. Is this all making sense? Yes.
I remember in college algebra,
Uh-huh.
we were able to, by like analyzing an equation, we can see if it had like a vertical asymptote and whether both sides were approaching negative.
Like what? Yeah. What both sides were doing? Uh-huh.
Yeah, but I've completely forgotten how to do that. I vaguely remember that it had to do with like looking at like the leading coefficient or something like that.
Yeah. There's ways to look at a rational function and determine if both sides are like going up, or if they're both going down, or one goes up and one goes down. And there's like little things you can learn to help you with that. The reason I'm not going to talk about that here is because we don't want to limit ourselves to just rational functions. Because rational functions are just polynomials over polynomials. But here we're not, it can be anything. It can be, like I'm going to give you some examples where it's not a rational function. So those steps or tricks that I would teach you would be out the window anyway. Right, we'd still have to do the limit, okay? Is that right? Okay. Let's try something else. How about this? How about limit? Let's go x approaches negative 3 from the left of x squared plus 9 over, x squared plus 5x, sorry, plus 6. All right. So what is the limit as x approaches negative 3 from the left side of this expression? First step, plug in and see what happens, right? All right, what happens up top? Yeah, negative 3, you square it, you get 9. 9 plus 9 is 18. So the top is headed to 18, right? And while we're thinking about it, that's a fixed positive number, yes?